we are going to burn some small fuel samples, solid fuel samples in a wind tunnel aboard the International Space Station. So what happened here is shortly before the incident, the building had gone through some renovation. So cladding were added to the building facade for energy and cosmetic consideration. So when fire entered this cavity space, the thermal expansion of the combusting gases and the flow confinement forced the flame to accelerate, and so it spread way faster than usually seen. Know that on Earth, hot gas rises, right? So fire is hot, so you unavoidably it associates with buoyancy flow. The problem about buoyancy flow is it's hard to characterize, and this complex flow may mask the underlying physics we want to observe. On the other hand, in microgravity condition, we eliminate the buoyancy flow, and instead we can impose, like in a controlled manner, impose a flow externally.
It's a small wind tunnel, so we actually force airflow past the sample, because without gravity, if you just left it burning, it would probably go out by itself, to be honest. So you need some airflow. But the nice thing that, as Yating said, we can control the airflow from 0 to any arbitrary value. So we can actually probe that scientifically, get resolution in regions we can't study on Earth at all. So it's very useful. So the main idea here is we would have the astronauts change the spacing. We move the black walls in and out, and we could change the amount, that the distance from the fuel sample to the walls, effectively making a narrow space or a wider space. As we heard earlier, the importance of the fire that we saw on Earth was a confined space. So we're looking at that effect on these flames.
The focus of this project is a protein that we call myostatin, which we discovered many years ago. And we showed that myostatin normally acts to limit muscle growth. And the dramatic illustration of this was that when we genetically engineered mice to lack myostatin entirely, the muscles in those animals grew to be about twice the normal size. So all of this immediately suggested to us the possibility that drugs targeting myostatin, that is blocking myostatin activity, could be useful in a wide range of conditions in which muscle loss or muscle wasting is a problem. And one way to mimic that type of muscle loss is in microgravity, as you've heard, where you get the systemic loss of muscle because of the inability to bear weight.
By testing this experimental drug, we are hoping to be able to test a novel therapeutic method of combating, really, both muscle loss and bone loss, not only in astronauts in space, but really for a lot of people here on Earth.
Imagine, if you will, you're responsible for operating a satellite that's orbiting our beautiful planet. And you need to track it and command it so that you can bring down data from it. Then it comes right above you, and then it leaves you. And that takes about 3 to 7 minutes. So you get a couple opportunities a day, and that's it. About a decade ago, we started investigating, well, what about using infrastructure that's already in space? And guess what? Have our data downloaded 24 hours a day, 7 days a week. This gave us an opportunity to formalize our first spaceflight collaboration with Mexico through Mexico's space agency. So mission objective number 1, demonstrate that we can use the infrastructure already in space, that we can connect with the global star constellation and have it download our data. Objective number 2 is give an opportunity, a spaceflight project hands-on opportunity to the next generation.
There's an electronic board that we actually designed, and it's in charge for the communication with the global star satellites. And for me to be participating in such a huge project was like only in my dreams. So it's actually like a great opportunity because it's also a new career in Mexico.
HISI, which is named after the bird, is an imaging spectrometer for Earth observation. It can observe more than 100 spectral bands. Using this technology, we can identify minerals and other things from space. Minerals has its own specific absorption band in spectral. Using this signature, we can distinguish and identify minerals. Distribution of minerals are strongly related to natural resources. The sensor developed in Japan is transported to United States and launched by United States rocket and attached to Japanese experimental module.